Thank you, Tim, for your introduction, and also to Tim and DREGS for invitation to make a presentation here. Made one earlier at noon, and I warned people then that about a 10 or dozen slides would be repeated. So for those of you who were here earlier, you can take a nap during those slides. But there are a lot of others here, so you're going to get to see something new. Antonio Ritas and I worked on this topic. This was a COVID topic. We've been talking about it for a long time, and finally we had a bit of time and started to get involved. Going to talk about alteration, epithermal porphyry environment, specifically, as Tim mentioned, advanced argillic alteration, the different environments, formation of what we're using the same name for, with particularly insight from active systems. And these hydrothermal systems are related to shallow intrusions, and these are magnetic fluids with variable amounts of New York water dilution. And I'm going to focus on alteration, but of course, these are major sources of critical metals, including everything that you mentioned at the end. That was an excellent overview. I really liked it and got something out of it. But every metal that's in short supply right now is produced from porphyry systems. Bottom line, in case you do take a nap, when mapping or logging, maintain mineralogy, textures, and morphology. There's a lot of trends towards lumping things these days, and I think that we are dumbing down all the information we're getting, using new tools, etc. We have to actually split rather than lumping if we want to get the benefit of all the information we're getting. And this is the paper that I mentioned that Antonio and I wrote. It's available open access, so you can, even if you're not an SCG member, you can go and have access to it. People are familiar with it. Solid diagram, some of the major epithermal porphyry deposits of the world. There's some obvious belts, metallogenic belts that are related to, in one case, through the Pacific margin, tertiary, Miocene to Pliocene epithermal, as well as now some porphyry deposits. Onto 0.4 million years of age. And then we have the Tethyan belt, basically Cretaceous through Eocene and younger, Southeast Asia through to Southwest Europe and Morocco. Paleozoic belts, for example, in Central Asia, Mongolia, but also Eastern US, Eastern Australia, they're preserved. And just thinking of it earlier, what is the
Saudi Arabia.
What is the Neoproterozoic deposit? Right? Nothing the name in 30 seconds is typical. Senior moment college. And up here, Neoproterozoic in Newfoundland. They're not metamorphosed. They could be 1 million years old. Also, Paleoproterozoic deposits in Finland, metamorphosed, but they are metamorphic, as well as possibly some in Canada. Okay. Since we're looking at these, well, that was showing the spatial relationship between volcanoes and epithermal and porphyry deposits. Of course, there's always a question of just relationship, but we take a look at one interesting portion of the volcanic arc here in the Banda Sunda arc of central Indonesia. We can see that numerous active volcanoes, Merapi, Bromo, Mount Bromo, Kawi Ijen, this pH less than 1 crater lake, acid crater lake with native sulfur mining in the area, nighttime view showing the high temperature flames around the native sulfur. That's the active arc. But the Eocene to Pliocene arc was basically to the south, 50 kilometers or so. This is related to, and I'm not up with the present tectonic interpretation, whether or not it was slab flattening or migration of the subduction zone, but possibly, most likely, it might be slab flattening to move the active arc to the north by 50 kilometers. Hadiyijao, Newmont deposit, very largely mined out now. Ilang hasn't been developed yet, also Newmont, or at least past tense was Newmont. I'm not sure of present ownership given the transfers these days. Bitu, but the Valley's discovery at Hu, the Onto deposit on eastern Sumbawa. Recent numbers just released at PDAC, 17.6 million tons of copper, almost world size yearly world supply of copper there, with all of the uranium mausoleum at 0.4. And not only epithermal veins occurring with some of these eroded centers, but also lithocaps. Lithocaps, and I'll define that in a bit, of advanced argillic alteration, some very closely related to known porphyry prospects. And of course, all of Onto is discovered below barren lithocaps stretching for tens of kilometers. So relationship between advanced argillic lithocaps and porphyry, particularly sometimes epithermal vein. Why? Because basically this environment, we're looking at either oceanic or continental subduction with slab dehydration and magnetism at the base of the crust. And at a depth of 10 to 15 kilometers, magma's ascending. And at about that level is where they are saturating with fluids. There's apophyses rising to 2 to 3 kilometers depth to the porphyry level. And shallower epithermal gold silver deposits and or base metals. This transition now is quite well documented and known. We have another epithermal district in extensional terrains, quite typical of northern Nevada, etc. But there are no known porphyry deposits here because it's completely different tectonic and igneous generation environment. But it still has some high sulfidation alterations, I'll point out as we're going. Well, as I said, some things don't make sense. Has somebody been playing with genetics here? And this is a genetic hybrid, which of course also occurs in geology. Or is it simply an overprint of a apple skin on an orange? And this is always a question when we're in the field. Is there some hybrid that hasn't really been described? Are we looking at something new, a variation on a theme, or is it an overprint, making it more complex? And the bottom line is avoid squeezing all deposits and alteration into end-member models, boxes, particularly models that yours truly may point out. You know, just make your observations and describe. Avoid putting things into models. Having said that, very conceptual model that Dick Silto published in 2010, you know, says a lot. And the reason that this all fits, the deposit styles, alteration, etc., is because it's all processes linked. The magma, shallow magma intrusions here, but you have a critical fluid from depth rising into the porphyry environment, 2 to 3 kilometers depth, about 5% salinity. Might be as high as 10, as low as 2, but not hypersaline. It could have up to 0.1%, 0.2% weight percent copper. You can see the tetragonal chalcopyrite here. When we directly analyze with laser ablation, ICP-MS, we know what these metals are. And then those fluids rise, they hit what's called the solvus. I mentioned this earlier today. We end up with hypersaline fluids, perhaps 50 weight percent. How do we take 5 to change it to 50 weight percent? I'd lose removing almost 90% of the liquid water as vapor. And so this is a coupling. You can't get the vapor without having the brine. You can't get the brine without removing the vapor. And thus, when the vapor ascends because it's buoyant, low density buoyant, it discharges from passively decaying volcanoes. That's telling us it's coming from this hydrothermal system, not directly from the magma. I worked with a volcanic gas chemist and magma specialist, Hiroshi Shinohara, in Japan for quite some time, and he demonstrated that you don't exsolve these low salinity vapors directly from magmas. There is this process in between. And if that vapor condenses, or I should say if, but when it does, in most cases that I've looked at, a half to a third of the vapor rising discharges, and the other half or 2/3 condenses into groundwater. And that condensate, which we'll look at in a moment, very acidic. It's responsible for forming the residual quartz, quartz anodite, quartz kaolinite, hypogene, advanced argillic alteration, and what Sillitoe defines as a lithocap, lithologically hosted advanced argillic alteration, capping the magmatic source of those acid volatiles. Of course, there's also the mineralization going on, porphyry. Some people prefer and observe much of the copper coming in during an early hypersaline fluid phase, potassic. There are also scar deposits, Zhaoshan's favorite, carbonate replacement. I'm learning more about even sed-hosted distal sed-hosted disseminated deposits. And then we have the environment. The upper kilometer or so, we may mineralize the residual quartz with epithermal gold copper and or have marginal intermediate sulfidation styles of veins, plus or minus base metals. In terms of alteration, particularly these 5 styles of minerals that are 5 styles of alteration are called grouped as advanced argillic. Julian Hemley defined this in 1964 to distinguish it from argillic, because people are calling basically everything argillic. Well, argillic is clays, but now we know we define the clays. But also, with short-wave infrared particularly, we can define almost all of these minerals because they have hydroxyl or sulfate bonds with a short-wave infrared signature. Kelmanite, loisite, dicite, graphite, and lucite, all luminosilicates. Luminosilicates with fluorine, zunite topaz, diaspore, aluminum oxide, and anhydrite. They're all advanced argillic alteration by definition. They combine with quartz and pyrite, very commonly present. And what I'm going to show is that these form in 5 separate environments. First of all, a hypogene environment of vapors with very reactive species rising, condensing, steam heated from H2S oxidation above the paleogroundwater table. Steam heated acid sulfate and weathering of pyrite, supergene oxidation. These are the 3 environments that we're most comfortable with. They all have different relationships, potential mineralization, epithermal as well as porphyry. But now, more recently, we've recognized that there's environment carbonic acid rich. It's basically responsible for a lot of the clay alteration around epithermal veins, both intermediate and low sulfidation styles. And another environment, porphyritic, is by definition advanced argillic, and yet it's forming at the transition of porphyry to epithermal. Very high temperature. We're going to take a look at how all these form and how they're related to mineralization. So we've been discussing the link between epithermal and porphyry. It's related to process. Look at a few more active hydrothermal systems, particularly focusing on processes and products, and then look at examples and interpret these alteration products, mainly the metals. The alteration, I'm not going to talk about metals today. And alteration mineralogy, as I mentioned, textures and morphology, have to be maintained during geologic mapping and logging, because this is what defines the environment, which then gives us information about erosion level, provide exploration targets for what's most likely the region, the area most likely mineralized. White Island, we saw this earlier today. High temperature fumaroles, discharges with dominant gases, 90% water vapor, but a couple percent SO2, CO2, 1% or less HCl, H2S. For the next slide, note these fumaroles here. We're going to look at a view from right here. These are low temperature fumaroles on the margins of these. And let's see if this works. Video, I didn't subsequently test. No. Come on. Where's my video? No. Before, I was just looking at it, but things have changed from noon. So sorry, these are very loud. You wouldn't be able to hear me talking. Because these fumaroles, these are low temperature fumaroles, only 300 degrees or so, but they're so loud that you cannot hear yourself talk. You cannot communicate with someone next to you working on these sampling. And if it had operated, I don't know if Will can figure out, anybody, right? Can you figure out screwing things up? Well, I shouldn't say screwing things up, changing the format. But I thought that this,
Yeah, it's probably
because usually it pops up when I go there. Usually get a pop-up for stock video. Even here, it's not active. So, okay, let's just go back. We can do without sound effects. I'll roar at you, it's really loud. And okay. So here we are at those low temperature fumaroles. High temperature, vapor condensates form pH of roughly about 1. They leach the rock, and they also leave halos of alkali at higher pH. And I guess this is not going to work either. Probably not. So, whereas here, this is a steam heated pool. You see this bubbling. Anybody's been to Yellowstone and Surrey, you see this bubbling, but that's not boiling. These are commonly 70 degrees, and the bubbles are CO2. That's because CO2 to H2S ratio in most of these cases are 10 or 20 to 1. So if you see evidence for, smell evidence of H2S, there's a lot more CO2 around. The H2S combines with atmospheric oxygen above the groundwater table and forms sulfuric acid, but pH of 2 to 3, simply lower concentrations than the H2SO4 that forms this environment plus HCl, pH 1. And so we're left with clays forming these muds around the pools. For those of you who visit Yellowstone or New Zealand, you know, there's at least one or two. It was on the mines field trip several years ago. Same alteration. Same alteration. Well, we go to La Coipa in central, just directions north of the main Maricunga district in central Chile. And here we see the 24 million year dacite dome on Latera Ferion, leached residual quartz, sulfides switching oxidized through here. This is what the rock looks like, not switching oxidized. We have, you can see the residual quartz with a buggy texture after Hedenquist that have been dissolved, some filled by sulfides, some filled by native sulfur. This was outcropping, the first deposit discovered in 1980 or 79. But Coipa Norte, as well as parts of Brecha Norte and Cancan, were covered by this blanket of white, friable material. Alunite and kelinite, opal at the base. This is steam heat alteration. This is friable, in contrast to this stuff, which will throw your rock element back in your face. And this is formed from vapor condensation above the paleo groundwater table. Well, Puran was discovered beneath a horizon of steam heat alteration, 5 kilometers to the northeast, with opal horizons and through here. And that was the companies, Codelco first, but then Placidome, followed up various anomalies and made this discovery. I think, no, I don't have that. That was earlier lecture. But there's a 30-meter thick blanket of barren steam heat alteration over the intermediate sulfidation Puran deposit, 5 kilometers from this high sulfidation district. Back to White Island, here during the period of lesser activity, vapors are still coming to the base of this crater, but the crater is now filled by groundwater, which is acidified. So we know we have a source of magmatic volatiles. pH 0.2. It's also low because of evaporation. It's quite hot, 50 to 60 degrees. You can see where it at times overflows, slightly neutralizes pH 0.6. And what's flowing off here is isochemically dissolved andesite, almost isochemically, except for silica. Silica in solution is silicic acid. Doesn't matter if it's pH 7 or pH 1, the solubility of silica is the same as a function of pH. Temperature and other factors affect the solubility, also affect the solubility. But in this case, silica is left behind. Otherwise, we'd have a big hole here of acid fluids dissolving the rock. Well, some silica does go to solution here, and this blue-green gray color here is due to colloidal silica in suspension. Eventually settles out, and here where the colloidal silica has deposited as muds, they've been exposed, they've mud cracked. But here in the case of Volcan Tuas, a similar acid crater lake of suspended colloidal silica. On the margins, you see very finely laminated siliceous deposits in places because there are some hydrothermal eruptions, blocks fall in and deform these finely laminated siliceous sediments. But this is basically telling us that we're at the paleo groundwater level. Well, if we go to a place like Yanacocha, ignore the tremendous gold deposits there, but walk over this 12-million-year-old dacite dome. Over the top, you see the vertical flow banding. It's clearly a dacite, it's clearly a dome. But on the margins, located about right here, are these finely laminated siliceous sediments. No plastic material, certainly no replacement. So these are depositional. They also have crossbeds, subaqueous. This was a moat of acid fluids around this degassing dacite dome. It's bare on the surface, although the under 200-meter deep Chaquicocha deposit is right on its margins. This is the Carachugo deposit through here. We won't go into discussing that. So this is a case where we now know what the paleo groundwater table was. And also in the district, Tony Longo, who toured me over here, he subsequently found many examples of finely laminated siliceous sediments with some classic material. You can see it also in drill core defining paleo groundwater table. Okay, that was a bit of an example of some active systems and their analogs in the extinct environment. Go to Japan, 41 active volcanoes. Virtually all of the active volcanoes have magmatic hydrothermal systems. acidic magmatic hydrothermal systems. 3 recently erupted, Takayama, Ontake, and Sachishirane, right there. These are the erupted products from those hydrothermal eruptions. Quartz kilnite product, quartz inite, pyrite product. Also, quartz muscovite, fluorite, feldspar, biotite. Sound familiar? These are, at least in this case, these are porphyry alteration mineral sediments. For such strani, erupted in 2018, crystallite, kilnite, pyrite, and porphyry. These are blizzing blocks being thrown out. So these are systems erupting through these are volcanic systems with hydrothermal eruptions from hydrothermally altered material. Here at Kusatsu-Shirani, we see the Crater Lake pH 1.1 again, magmatic volatile condensation, and MT surveys shown here. Brittle ductile transformation, because basically this low resistivity, less than 1 ohm meter resistivity, this is due to hydrothermal system, not due to magnets. There probably are some dikes through here. And let's see, black dots are sin eruption. So sin eruption, there was seismic activity through here, stopped basically at the top of that high temperature zone, or I should say where they end is where you're now going to ductile behavior. The gray, I can't remember if the white are pre and the gray are post eruption, seismic activity. So there's a huge hydrothermal system at 1.5 kilometer depth below that volcanic environment, and at times it'll erupt magnetically as well. Fukushima, south of Nansatsu, south of southern Kyushu. Here we have a 1,000-year-old rhyolite dome, again, just like White Island. These are isochemically, except for silica, dissolved rhyolites. In this case, we collect samples of the vapor. This is 770-degree fumarole right here with acid gases, which we have to protect our skin from. So that's why we're wearing rubber suits and having a rebreather. Another video that we can't show, but these are only 200-degree fumaroles, but we have some up to 880 here. This is the reaction. SO2 disproportionately to sulfuric acid with H2S, H2S, H2SO4, and HCl. At high temperatures, above 300 degrees, those acids are associated. But cooling to 200 degrees, you get about 50 times dissociation of the acids, such that we now have hydroxyl ions, hydrogen ions to attack the rock. 300 degrees, these acid species are not reactive. 200 degrees, they're extremely reactive. pH less than 1. And that's all due to cooling. Crystallite, up to 97% silica. Here's the rhyolite. Bernd Greenbach is looking at these vapor condensates having leached everything from the rock, leaving behind residual amorphous silica, eventually crystallizing to quartz. Alunite, some mountain rhyolite, other clays through here, less than 2 ppb gold, except for one sublimate of 29 ppb. This is a barren alteration scheme. There is Satsuma on the horizon. Here on shore, that's an air, unfortunately, 4 million year quartz alunite at Iwato. And here we see the residual quartz in extension, about 900 meters long, with narrow halos of quartz alunite. Here, knife sharp residual quartz to quartz alunite. That's Urashima standing right next to the contact. We can see the quartz alunite going out to dicite, kilnite, some perovskite. Feeder zone here. And that's the point of this cross section. This looks like a single silicic body with various gold bodies greater than 1 gram gold. But when we look at it in cross section, we see the the andesite host, there are structures that are controlling the residual quartz, the quartz allied halos. But when those fluids descended into the unwelded tuff, they mushroomed out. And this was the first recognition by Professor PhD in 1981 of a lithology control, i.e. lithocap control on the alteration. So basically, the geometry of lithocaps are lithology controlled residual quartz, of course, particularly distal positions, barren formation. All lithocaps have some type of structural feeder or margin of a dome or a diatreme, what have you, but not necessarily feeder zones have lithocaps, like at Summitville. Summitville was structured through a monzonite dome, no lithologic permeability, no lithocaps. We discussed that earlier today. The residual quartz from Summitville, quartz allied halos, this monzonite, and you can see buggy quartz after coarse and fine finicrous. And over the top, steam heated alteration due to H2S oxidizing above the groundwater table. So these are two environments, very distinct alteration styles. The one thing about this, the hypogene alteration is barren. This is the muscovite stage, the muscovite overprint stage of the porphyry that brings the metals in, may bring the metals into the lithocap. Well, let's take a look at back in Japan here, Hiroshima, Iwayama Dome, Dayside Dome erupted in 1700s. I remember, but everything erupted in 2018 with acid features. Hot springs around the margins, pH as low as 0.8. Also, volcanic eruptions at Shimoidake as recently as 2011, 2018. And it also has very low resistivities, right below the Iwayama Dome hydrothermal system. And these are the seismic, so basically 400 degrees, 350, 400 degrees, ductile behavior, about that depth, 2 to 3 kilometers depth. On the margins of this system, this very acidic system, there's a neutral pH geothermal system generating geothermal electricity. You cannot generate electricity from these acid systems. These are neutral pH, and also the silica sinters indicate that. So this is just an introduction to show that we can have neutral pH systems on the margins of these intrusive acidic systems. Now, if I had more time, I would discuss this particular geothermal system interaction, but this is just illustrating that relationship. We're going to move, change country, change tectonic setting to New Zealand, double volcanic zone. Take a look at Champagne Pools, look at center here, like we saw in the last view. But in the hanging wall of this structure are vapors discharging steam heated alteration related to H2S oxidation. We go to an old district like the Sulphur Mining District. My first consulting job with Freeport in 1982, and we were looking at steam heated alteration in this area. A lot of native sulfur formation, allignite long structures. Fast forward to, not sure when this was developed exactly, but it was at the time the mining called Lewis Croton House called Highcroft, 30-meter thick horizon of steam heated alteration, opal, allignite, kaolinite, jarosite, opal at the groundwater table. Bar, because mercury is the only element transported in these low temperature vapor with gold mineralization at depth. And we were very excited because there wasn't much of a metal anomaly in this alteration. There was a silica center, lower elevation, kilometers to the north, and I didn't know much in those days. Now we realize that there was an upflow and then an outflow along the hydraulic gradient to the north, where finally hot springs were discharging at. Well, anybody visit Yellowstone? Yeah. If you hike down into the Grand Canyon of the Yellowstone. Yeah. This is going to be one of our stops in after the SGA meeting. This is a painting by Thomas Moran shown in Congress. This is the reason, these paintings of Thomas Moran were the reason that they formed the national park here. People, certainly Congress people hadn't visited this area. There were no photographs. There are hot springs depositing silica sinter at the bottom of this valley. 10,000 years ago, those hot springs were discharging up on the rim. Silica sinter. Also, what's exposed now by river erosion is illite pyrite. Pyrite oxidized, that's the red and yellows. Quartz plus minus argillic. Oh, it's fairly familiar. And kaolite up on the rim, opal horizons, so everything, just as we were seeing at Champagne Pool and in the hanging wall. And from Peter Larson, this is the picture at that time. Fast forward, and after glacial retreat, the Yellowstone River has cut down almost 300 meters. And as the river is cut down through the system, the groundwater table has followed the river level, and in turn, sea mean alteration is followed. So we end up with this overprint of even light pyrite quartz argillic alteration. And any metal anomalies here are being overprinted by the sea mean alteration. So we can get that acting on the system. So overprints. Back to the Canyon Zone, Champagne Pool, White Top located here. This is Brahms hockey system with the Oaxaca pool, and through here, weekly boiling Oaxaca pool, beautiful silica sinter. These are production wells discharging, actually cleaning them out at that time. Some pilot tests. Of course, we don't open them up. Well, right now, they're generating power. All that high pressure vapor goes through to the power station. A section, basically north-south of the system. I compiled the paleoisotherms in looking at paleo, I talk about paleo so often, the measured present-day isotherms. And Sir Simmons came along a bit later and looked at the alteration. We have adularia in the upflow zone, basically in the upflow boiling zone, depositing adularia with illite, basically defining the 200-degree isotherm, illite smectite and lower temperature smectite being on the margins, the carapace, smectite stable at less than 150 degrees. Exactly what you predict. If you eroded this, that alteration pattern would basically be directed towards the upflow zone. This is where Oaken Pool discharges. This is the high temperature wells are basically tapping this upflow zone. We have our steam heated pools with thin horizon of acid sulfate, H2 to 3 pools, and then we have well 6. Well 6 was discharged. When it was discharged, it didn't look like this. You open it up, and it was a CO2-rich froth. Does anyone like beer here? Not to change the subject, but of course, what's the pH of beer? Does anyone make their own beer? pH? I got somebody last time to answer it, they knew. But what's in solution? What happens if you shake a warm can of beer and go CO2? CO2 forms carbonic acid. Carbonic pH of beer is 4 to 4.5. If you're into German beers, heavier beers, lower pH. Let's say 4.5. Just imagine if you put feldspar into beer and heated it up to 200 degrees, you'd form kiln. And that is why, oops, For some reason, there should be a animation that's not showing up here. There's kaolite, this well, kaolite, anchorite, this well, kaolite is set this well, this well. There's a carapace of kaolite siderite very deep. It's not due to, as the sulfate water descending down, it's due to this carapace of CO2-rich, carbonic acid-rich fluids. And through here, we lost this well. The reason we learned about this was we lost this well 25 at 455 meters depth, casing break from the outside in. The 401 stainless steel was completely converted to hematite by these carbonic-rich fluids. And I was given the job to sort it out. Fellow, let's see, machinist made a sealed downhole bottle. We sampled this, brought it up, and let go the pressure into a sodium hydroxide solution. And for 20 minutes, we bubbled CO2 into the solution. It was over 1.5 mole, converts to about pH 4.5, or say 5% CO2 solution. That was the cause of that casing break. And thus, that was the reason that we recognized these CO2-rich fluids responsible for the CO2 and anchoring. Well, what does it mean? I mean, so what? Unless you're wanting to protect your casings. Well, here, Pol Chukka, Cretaceous age external deposit, discovered by Slava Zakuskin on the last traverse of the season. Here's his field vehicle with his early warning devices for Kodiak bears, translate to grizzly bears, hungry and mean. And when I've been working up there, there's one fellow that does nothing but carry a high-powered rifle, and you never see him looking at you. He's always looking behind you, which is good. Beautiful, classic. Come out of a Miocene age epithermal deposit in Nevada with colorful banding. Here's the gold. Red is about 30 or 50 ounce of 50 grams. Silver as well. Notice in the north extension down offset. Well, that is basically a fault downfall. In early drilling, we weren't doing any shortwave infrared testing, but subsequently we started to work on clay mineral zonation up here. Suddenly we see 200 meters of smectite, low temperature smectite. Then illite in red, and then illite kaolite. What's that kaolite doing down there? Humidity alteration descending? No, that's carbonic acid fluids. That's responsible for the illite and the kaolite. We look at a cross section right through this position here. You see the smectite zone, illite kaolite zone. When you get into the chloride zone, keep drilling, because that is basically right in the hanging wall. You call it, these are almost vertical veins, but right in the hanging wall of the high-grade vein. So we can now explain why we have kaolite and this illite. It has nothing to do with the late overprint. So, transition zone. We've looked at sediment alteration, we've looked at hypogene alteration, we've looked at carbonic acid overprint, and now transition. Base of the lift cap. Here at El Salvador, very extensively studied deposit below the surface. Essentially, this was discovered in the second drill hole. Long story, but I'm not going to go into it. And as a result, relatively little study of the surface. So my colleague, Asushi Watanabe, and I, we fortunately working for the Japanese government, who had a memorandum of understanding with Codelco, government to government, and mapped the area, mainly Watanabe-san. This is, of course, this is originally biotite and sulfides here, but the biotite had been overprinted by muscovite, 2M1 muscovite, plus andalusite, sulfide supergene oxidized. And then the top of Indomuerto is porphyry. Justice and Hunt in the 1975 paper suggests that these were steam-heated acid fluids descending down and being heated and at higher temperature forming peroxide. Not the case. These are magmatic fluids. These are muscovite transition peroxide. Earlier, when we were talking about this KH ratio, we were talking about getting into residual quartz field. We're getting a very high hydrogen activity, getting into residual quartz. Before that, we were in alunite diaspore field. We potentially be stable with peroxide at higher temperatures. But let's not think about that right now. Let's just look at Julian Hemley's 1964 diagram of mineral relationships. Muscovite and lucite, you see that the two minerals coexisting in section and transition to peroxide. Simply cooling. We're not making these fluids acid. We're cooling a muscovite and a lucite, or just muscovite fluid, into peroxide stability at relatively constant KH ratios, potentially even dictite stability. And we do have dictite at the margins of the L-sulfur system. Simply peroxide in dark, this SEM image, replacing along the cleavage planes the muscovite. It's a retrograde reaction. Nothing to do with acidity. And yet, this would be called advanced argillic alteration. My point is, be careful what you call advanced argillic alteration, otherwise you're just lost. Report the mineralogy, the textures, the morphology, etc. This is, I think, our final example here. Quartz alunite alteration. It occurs here in the Ancaina district in northern Luzon. It occurs right at the uniformity between volcanic classic basement and the dacite pyroclastics, all along here, 7 kilometers of cliffs, where they have been exposed by river erosion. We look at a long section here, long and then cross section, long section, far southeast porphyry deposit, right at that unconformity is where we have the residual quartz of Lepanto, quartz alunite also along that unconformity. Basically, center fluids. This is the porphyry that Goldfields drilled up from the 700-meter level for old underground workings. Rehabilitated. They drilled below sea level, drill up the far southeast porphyry, 600 tons of gold, 5 million tons of copper, 1% copper, great shell in orange, 0.7 grams in yellow, the 100 ppm moly in blue. Antonio Rivas dated 5 samples of biotite here, all within 1.41 million years, within 40,000 years, 2 sigma error. And of course, that was the brine at depth, vapor ascending. There would have been some vapor discharging. But at about 1.5 million years, the age of this edifice, strong hydraulic gradient to the northwest, and condensing some of the vapors, 5 samples of alunite, 1.42 million years, plus minus 60,000 years, 2 sigma error. The same ages. Why? Because they're coupled in terms of process. Vapor, the stench from the fluids creating the biotite, is what's creating the alunite. Subsequently, and that's what created this residual quartz barren stage, vapor coupled to the biotite. This is photographed from Zhaoshan Shang, who worked on this deposit. Subsequently, well, let's see what's happening. Oops, screw. No, I guess, yeah, we have reasonable animation here. The white mica overprint of the porphyry, 1.35 to 1.3 million years, that fluid salinity 5% was able, low enough salinity to sufficiently buoyant to rise into the residual quartz and mineralize it with gold and argite. And that's the system. Victoria veins, slightly younger over here, formed on the margin of the porphyry. And this shows the base of the lithocap. One of Zhaoshan's students from Australia, Michael Calder, when Zhaoshan was in Australia, base of lithocap. Of course, an end alteration. And then Michael logged 10,000 meters of the 100,000 meters drilled through the porphyries. We see the overprint of white mica chlorite elbite on the early potassic alteration. You can see the highest grades of copper and gold are within the white mica overprint. And that white mica overprint right between the lithocap and the white mica is dominated by perovskite, as well as some other luminosilicates, diaspore as well, alunite. And so this is not acid alteration from the lithocap. Again, this is white mica fluid ascending and cooling and giving you this overprint. So, see, I'm a few minutes over. I added 5 more slides. Can I finish 5 more slides? Okay. Anybody who has to go someplace, don't feel that you're going to insult me by leaving. Come back and look at an overview of Yanacocha. San Jose, we're going to, these are all deposits here, up to 25 million ounces of gold produced, Yanacocha Norte. Cooperville Valley, Copper Valley. One what's called Copper Valley. And we're going to take a walk from San Jose down into Cooperville Valley. And basically, we left residual quartz behind. We're now in quartz alunite. We're walking down 300 meters vertical into the valley. Halfway down the valley, you see perovskite. It was called patchy silica, but it's not silica that's patchy, it's perovskite patchy. It's a nodular replacement of perovskite after silicious rock. And if you get to the bottom of the valley, the Thomas Klein, German, who drilled this area, one of the geologists drilled in KUP3, discovery hole, porphyry-style veins at depth with muscovite, faulted through here, and then perovskite, kelnite, alunite, and the same patchy texture of perovskite after basically replacing the silicious rock. Why? Perovskite has a 2-to-1 silica aluminum ratio. Muscovite has a 1-to-1. To form perovskite from muscovite, you need a lot of silicon. In this case, it's getting it from dissolution, nodular dissolution of the silicious rock. And here at the bottom of the valley, we see some stockwork, quartz vein stockworks with white mica overprinted by perovskite alunite. And the Kufdal porphyry that was drilled. The biotite has a age of 10.73. The alunite, San Jose and Cory Mayo, 10.73, 10.76. This alunite, these lithocaps formed at the same time as the porphyry. We have no lithocap over the top of this porphyry. Why? I mean, residual quartz and quartz alunite. Because it was too hot through here. It was white mica perovskite dominated, easy to erode into a valley, whereas the cooler upflow, both in the direction of San Jose and Cory Mayo, formed the quartz alunite and residual quartz lithocaps on the margins of that porphyry. Now, that's suggestive, cannot prove it, but at least dating-wise, it's a consistent interpretation. Either that or there's another porphyry responsible for here, another porphyry responsible for this lithocap, both of which were the same age as this porphyry. Simplest is these lithocaps are related to that porphyry. So I would say don't drill directly below your best mineralized lithocap. Imagine going back to Lepanto. Lepanto, 90% of Lepanto is offset from the underlying Parthenope porphyry. Only if you drilled at the furthest southeast end of Lepanto, the lithocap, would you have gone through the porphyry. And it's because this simple hydraulic gradients in the epithermal environment coupled with the increased reactivity at lower temperatures down the hydraulic gradient. So, silicic and quartzite lithcaps form on the shoulders of porphyry deposits. I can show you several examples. This was an aside about the formation of the patchy texture here, Valeria Garcia, studying Milagros porphyry prospect just south of Lagunas Norte in northern Peru. Brophyte replacing embayment of the quartz. Why? Because we need that silica, as I mentioned, to form brophyte on muscovite. And we see these sections all over the world. They're in the brophyte zone over the top of Oya Tokwe, in Turkey, in a lithocap adjacent to a small porphyry. And here, within 15 kilometers of a world-class porphyry deposit in central Chile, which still remain nameless. Patchy brophyte, or where it's eroded. So if you just call that brophyte advanced argillic, you might put yourself in a different position. And the final slide here is Newmont geologists came to Saracopinas, 10 kilometers to the east of Yanacocha. They sampled this quartzite lithocap. It was, to all intents and purposes, for them, barren, less than 0.1 gram gold. Subsequent group came in here, and a young practicante, trainee geologist came over, lifted up the soil horizon, didn't know what the sheet veins were, brought a sample to the chief geologist. These were samples of porphyry, sheeted porphyry veins of the parole gold copper porphyry. That was a discovery. 640 million tons, 0.3 copper, 0.7 gold. And when it was dated for 15.8 versus 16.06 for the alunite with error bars, these overlap. Again, maybe there, and Daoshan has worked on this. There's some suggestion that something to the north never been sorted out, but at least in terms of overlap, one question is, if these are so close in age, why isn't this very resistant quartz, silicic resistant quartz lithocap? Why isn't it also present over the top of porphyry? I argue because it was never there in terms of this resistant quartz down there. This probably was a much more erosive alteration. So, and the final, of course, is post-hydrothermal oxidation of pyrite. It's crystalline, but looking at some of Will's samples today, that alunite along fractures were with iron hydroxides, clearly supergene, post-hydrothermal keelite and alunite. Again, that's actually alteration, but not telling you anything unless you discuss the neurology, the textures, morphology, etc. We have our steam-heated acid sulfate, another steam-heated like carbonic acid-rich, pH 45, but stable with respect to clays and kilnite. Hypogene, of course, very acidic, related to magmatic volatiles, acidic magmatic volatiles, pH 1 to 2. Then we have cooling from white mica to brophyte, constant KH, not really acidic in terms of what we think of when we think of advanced argillic. And then also supergene, where in fact we can have pH 0, large amount supply of pyrite oxidizing. So these are all advanced argillic, but I prefer to maintain the mineralogy, texture, morphology, and avoid names such as advanced argillic and argillic. And I think you'll get a lot more information from your alteration if you do that. Sorry for running over. Thank you very much for your attention, and I'm glad that earlier today, there were questions from people that, to a large extent have as much gray hair as I have, even more. We didn't get anything from younger. So, do any students have questions?